Welcome everyone. Today we will be discussing about queuing models. Queues are everywhere. While going to a coffee shop, waiting, going to attend say, going to buy a ticket to a concern, a railway platform, uh, security checking at airports, and so on. So there is a calling population. So from where the people are coming, they are joining a line, and finally they are being served. So this whole thing. So there are three main components. One is the server, one is the customer who is coming and forming this queue, and this queue length. So this together forms a queuing model. And in this particular chapter, we will be discussing about the queuing model and for what purpose we can use these queuing models. In fact, queuing models are a powerful tool for designing and evaluating the performance of queuing systems. Now, what is a queuing system? So, wherever these sort of queues are formed, we might be interested in several performance measures like server utilization, length of waiting lines, and delays of customers. Like coming back to this figure, so if you are going to form a say counter system or service system, then obviously your first question will be how much servers I should install. So whether one will be sufficient, two will be sufficient, three will be sufficient, four will be sufficient. In order to answer that you need to have answer to certain questions like what fraction of time, say if it is one server, what fraction of time this server is free. If it is two server, what fraction of time it is free. If it is three server, what fraction of time it is free. Then what is the average length of this queue if there is one server? What is the average length of the queue if there are two servers? What is the average length of the queue if there are three servers, and so on. And if the length increases, the waiting time of this population will increase, and then the population or the person, the customer, may not be very interested in joining that particular queue, and say in a business that means losing a business, and so on. So for relatively simple systems, easier way is we have a mathematical formulation. So we can compute mathematically how how many servers and what can be the length if the length has to be finite. Then how we can what will be the optimal parameters of that queuing system. But if it is really a realistic model and complex system, then simulation will be a better tool strategy there. Characteristics of a queuing systems are, so the first the most important thing are in a queuing system there are two most important elements. The first thing is customer. A customer refers to anything that arrives at a facility and requires service. Examples may be people, machines, trucks, emails, packets, frames, and so on. And server refers to any resource that provides the requested service, like repair person, machines, runways at airport, host, switch, router, disk drive, algorithms, and so on. Let us consider certain examples. Like in a hotel, the the system is the reception, and the customers are people, tourists. The server is the receptionist. In a hospital, patients are the customer, nurses are the server. At airport, airplanes are the customers, and the runway, while they are taking other going for say landing in or take off, the runway is the server. Production line, the cases are the customers and the case packers are the servers. Road network, so car are the customer, traffic light is the server. In a grocery store, shoppers are the servers, checkout station is the server. Computer, the jobs or the programs which are submitted to the jobs to the computer are customers, and CPU, disk, CD, these are the servers. In a network, packet is normally a customer, and router, switches, all these are servers. So one by one, let us see what are the different component and how those components may affect a queuing system. So the first thing, if you just go back to the first figure, we found was the calling population. So what is the or the servers basically, the customers. So what is the characteristic of the calling population? The calling population, the population of potential customers may be assumed to be they can be finite or infinite. Now, how they can be finite or infinite. So, if the arrival rate depends on the number of customers being served and waiting, is basically called as a finite population model. Like in case of if a company has got just one corporate jet, and if that is being repaired, then the arrival rate becomes zero. So that's a finite population model. So if there are only 13, say 30 machinery, and there is one mechanic who repairs the machineries. So if 5 machineries are at fault, then the arrival rate will be dependent on 25 only. And if all 30s are faulty, the arrival rate will become zero. On the other hand, in case of an infinite population model, the arrival rate is never affected by the number of customers being served or waiting. Examples: in a large population of potential customers, like in a ticketing system, at a hotel, say a reception system. So it doesn't mean it never say states that if a certain number of customers are waiting, then no more customers can come, and so on. So the calling population may be finite or infinite. Next is the system capacity. So what is the maximum length we can apply? We can allow that allow to be the length of that particular queue. So if we go back to this figure, so this waiting line. So is there any limit on this waiting line, or this is basically say infinite again? So we can have a system capacity, or a limit on the number of customers that may be in the waiting line or system. So it may be of limited capacity, like an automated car washing has only 10 cars to wait in the line to enter the mechanism. So if 11th car comes, it has to leave the system. So it cannot enter into the system because there is no place where that car can be parked. So if the system is full, no customers are accepted anymore. So the figure looks something like this. So there will be fixed slot in this waiting line, and there will be server. So once this slot is over, so like in a barber shop, so if there are 4 chairs, so 4 people have come, say, and including one whose haircut is being done, then if the 5th customers come, he has to leave. On the other hand, there can be unlimited capacity also, like concert ticket sales, with no limit on the number of people allowed to wait to purchase ticket. So this waiting line can theoretically go infinite. So there is no limit on that. The next thing is, okay, how this customer. So now we have a queue, so a length of a queue, finite or infinite, and we have certain customer calling population. So how from that calling population people are coming and joining this queue? So we define this by arrival processes. So arrival processes can be of 2 types depending on how the arrival happens. So the arrival can be random arrivals, where inter-arrival times are usually characterized by a probability distribution. So if a customer has come now, where the next customer will come is not determined, is not already fixed, is not already scheduled. So customers can come at random time. And most important model, which we will discuss in this course also, is a Poisson's arrival process with a rate of lambda, where a time represents the inter-arrival time between customer n-1 and customer n, and is exponentially distributed with mean 1 by lambda. So if at tth time a customer has come, then at next time, so t plus 1, another customer, so there is a probability that, say, in between t and t plus 1, so there can be a lambda number of customers who can be entering into the system. Scheduled arrival. So the second type of arrivals can be scheduled, where already inter-arrival times are fixed, or say plus minus a small random value, like a fixed scheduled visit to a physician, or airline flights arrival to an airport or departure from an airport. They are mostly scheduled, and so there is a plus or minus delay of such small amount. Next thing is once the people are in there once the customers are there in the queue, how they are behaving. So The action of customers while in the queue waiting for the service to begin is basically defines the queue behavior, and queue behavior can be balking. So if a new customer comes and sees that the line is too long, he or she may never join the queue and immediately leave that system. So that customer is called as balking. The another one is reneging. So a customer comes, joins the queue, waits for some time, and then sees that the queue is moving very slowly and it will be too late for him or her to get the service. So after joining the queue, they leave the system after a certain time. They leave the queue after a certain time. So this is called as reneging. And third type of customer behavior or queue behavior is jockeying, where a customer moves from one line to another line if there are more than one lines, more than one parallel servers, and customer jumps from one line to another line in a hope of getting smaller waiting time is called as jockeying. So in case of a finite queue length, bulking is basically a fixed. Bulking becomes very common because whenever the number of parking slots are fixed in a fixed parking case, the newer customer has to bulk only. Otherwise, in infinite case, the bulking will be very rare cases if the queue is not too long. Queue discipline. So how, if the customers are there waiting in the queue, in which order we will take the customers and serve them? So the logical ordering of the customers in a queue that determines which customer is chosen for service when server becomes free it defines a queue discipline. And the queue discipline can be FIFO, first in first out. That's normally what we know as a queue in computer science. So the other can be LIFO, last in first out. So we can select the last person who has joined the queue to serve first. Not usually done, but may be done. Service in random order. So we can select anyone and we can serve them. Shortest processing time first, or we can assign certain priority to the customers and service them accordingly. The last component is service times. So just like arrival time, the service time may be constant or random. So if it is a random one, so normally the random one is denoted by an exponential distribution, and it's with a mean of mu. So we'll see that later on. But it can be fixed also, like in an automated car system where the fixed time is there. So car will enter and after a certain amount of time the processing will be done and go out. But in a normal, say as a cash collection center, ticket booking center, registration desk, the time will not be fixed. For every customer, they might have, say, unique entries, and it will take say plus minus a mu amount of time to serve them. And a queuing system consists of a number of service center and the last, obviously the last component is the number of servers. How many servers we have placed in the queuing model. So there can be C number of servers. These servers can be placed in parallel or in normally working in parallels. If they are in serial, they will form different queues only, the levels of queues. To represent the different components of different characteristics of the queue or different types of queues, Kendall devised a notation, and it is typically represented by these 5 letters A, B, C, N, and K, where the first component represents the inter-arrival time distribution. So how the customers are, basically what is the characteristics of arrival time. So arrival time characteristic is denoted by the first letter. The second letter represents the service time distribution. So what is the characteristic of the service time? So is it a fixed one, or is it is it a probability based? And if it is probabilistic, what is the distribution which defines that service time? C represents the number of parallel servers. So how many servers are installed in that particular system? N represents the system capacity. So what is the length? What can be the maximum size of the length in that queuing model? So queue length, what can be the maximum queue length in that particular scenario? And K represents the size of calling population. So if the population, if the arrival is from a fixed finite length population or infinite length population. So normally to start with, normally we will start with say C equals to 1 and N and K, that means the system capacity and the calling population, to be infinity. And in that case, if both of them are infinity, we drop these two symbols. So we can write then A slash B slash C. And let's see, A, B, C also has different notations, symbols for that. For example, for A, normally we can use either M, so if it is exponential distribution, or Poisson's distribution. Because M represents a Markovian and memoryless property of all these exponential and Poisson's distribution. Or A and B can be represented by symbol D when it is constant and deterministic one. It can also be represented by EK and a long distribution representing that the calling population, so the arrival time and the service time is following a long distribution. By H if it is following hyper exponential distribution. And G general, we do not have much information about that. An example can be M, M1, infinity, infinity. Or as we told that these two, if these two last two are infinity, we can drop them also. So if it is MM1, that means it's a single server with unlimited capacity and call population. And inter-arrival time and service times are exponentially distributed. So basically they are Markovian and they follow a memoryless property. Some examples are like a customer service desk in a store can be represented by MM1 if it is a single customer service desk. An airline ticket counter, because there are so many ticket counters, so we can represent it by MMS. S represents the number of ticket counters. If it is an automated car wash, then we know the arrival rate can be anything, but the service rate, car wash rate, since it is automated, it will take fixed amount of time. So M/D/1, assuming that we have infinite number of car parking and there are other cars, there is no limit on the car which is coming to the system. Calling population is infinite. Another one like auto repair shop. So in case of auto repair shop, again the auto can come at any time, and repair time can be, sometime it can be very small, sometimes it can be very long. So it is very hard to define that distribution. So we can make it by the general distribution. So MG1. And if it is a limited population, like if we have only 12 machines which can break down and which has to be taken to a system, but there is no length on the queue, so then we can and then there are many parallel servers, so we can represent it by MM/S/infinity/n. So this defines the models. Now what exactly we will get from this model? So once we have the model, what exactly we are trying to find out? So as we indicated at the start, that we will be interested in finding out how many times or what fraction of time the queue is, or basically the server is idle. Or another way, we can find out the probability of 0 customers in the system. So what is the time, or what is the probability that there are 0 customers in the system, meaning the server is idle. Similarly, we can find out exactly what is the probability that there are exactly n number of customers in the system. N can be any number, any general number. What is the utilization factor of the server, probability of all servers being busy? What is the average length in the queue, and what is the average length in the system? That means queue plus the customers who are being served. Similarly, what is the average waiting time of a customer, and average waiting time of a customer in the queue, and average waiting time of the customer in the system. That means queue plus the service time. So these are the values, or these are the performance measure we will find out from any given queuing scenario. So for the rest of this course, we will follow that. We will see that we will assume that the arrivals as well as the service follow. Arrival follows the Poisson distribution, and service follows the exponential distribution. And we have a FIFO service, so first in, first come. We will consider both cases of unlimited queue length and finite queue length, and we will consider the steady state conditions. That means we are studying the system performance when the system is running for quite a long time and has achieved a steady state. So for today, we'll stop here. Next day, we'll directly move on to discuss, move on to find out how to find out this P0, Pn, and derive all these equations. So thank you for your attention for today, and hope you are enjoying this course, and we'll keep on posting. Thank you.